Yeah. It's about 20 years ago that the last time I gave a sort of a tutorial using a programming language. So I might make some mistakes, or it's also the first time I'm doing this about this topic, so it is not a rehearsed tutorial. Or so forgive me if I forget things or make mistakes, and please interrupt me if you think that I'm forgetting something or you don't understand something. I regret I have to be talking quite a lot because there is a lot of things I have to explain before you can get up to speed. So it won't be like Steve's tutorial that you won't be quickly doing this. I have to explain a lot, so I'm sorry for that. Also, I prepared this with a terminal so we could do some live coding. But I found out that it is a bit hard for me because I don't have eyes in the back of my head. So I can show you the terminal, but I can't see it. Or the other way around. And for doing that I have to mirror my display, but then my presentation won't work. So what I've decided is to use the second half of this presentation, after the lunch, to do the coding. Then I switch my laptop in mirroring and then we can do it together. And the first half we do it like this. And if someone of you is actually running the code on your laptop and have questions or remarks or whatever, then well, feel free to jump in. Did some of you actually use the code space on GitHub? Because did it work?
Well, I just opened.
Okay, so that's. Yes, you have to be signed in. Yeah, because I tried it a couple of days ago and it didn't work anymore. So I can't give any guarantees. I think the pip install instructions are maybe the easier way to go, or a bit safer. Okay, great. All the materials I'm showing, all the snippets in the presentations and all the examples and all the exercises and challenges are all on GitHub. So you can, if you apply one of those two methods to get the materials, you have everything that's on the slides and that we'll be talking about. Also the answers to the solutions are also part of the slides. So everything is basically in there, and you could review everything later on if you want to. In-source testing is something I started doing a couple of years ago because I got rid of the testing frameworks that I was using at that time. And when I got acquainted with ASP, Answer Set Programming, I thought, well, it might be a nice combination. And it is a nice combination, so I really like to share my experiences with it today and hear from you what you think about it. As I said, there's a lot of contents in this presentation, and I reviewed it together with Nico, and then I thought I have to change a lot of it. And what I chose is to introduce ASP as we go, because otherwise it is just too much information. So I will give you all kinds of real code examples from ASP, and then as we progress through the presentation, I will gradually cover all the topics that you need to know. A little bit about myself. I'm just nuts of programming. I can't help if I see an interesting programming language to try it out. And I really like do all kinds of meta things, or try to push the language to its boundaries and see what else you can do with it. I've been giving a presentation on the British conference about delegation in Java. Java is inheritance based, and I thought, well, I hate inheritance, I like delegation better, so I made delegation in Java and presented that. That's the kind of things I like to do. I have a sort of a second life as an extreme programming enthusiast. I started doing that a couple of years ago, and you can guess that's one of the main reasons that I really am focused on doing unit testing, because I really can't live without them anymore. These languages are dated back from almost 30 years, I think, and are only the languages that I really did substantial things in. So they're all of them, I have used them in real applications that work on real world problems. Closure is a functional one. And as I said, programming is a logical one. I also did some Prolog, but that was only in a study context, so I don't mention it here. And all the others are basically imperative languages. I started a new project beginning this year, and that had to do with railway protection. It's called interlocking. And they asked me to solve a big problem for them because all the railway interlocking is defined in logic, which is zeroth order logic, which means there are no variables and there are no sets, or it's really primitive. And they have text documents written in Dutch, and these are kind of specifications that lead to an implementation written in Boolean logic. And I can show you that. This is the kind of Boolean logic that they have to produce that is eaten by machines like programmable logic controllers, PLCs. And they have to read a Dutch document and produce that, and have to do it over and over again for each switch, for each signal, for each emplacement. They have to redo that, interpret the Dutch text, and rewrite it and review it. And they want to do some automation. So what I thought, well, maybe it's a nice idea to have this zero order logic generated from some higher order logic. And for this higher order logic, I chose ASP. And that's how it got started. Because the idea is, if you cross-compile that, then you can forget about that logic world. And if you have everything in ASP, you can start do unit testing, you can start do formal methods. And well, everything will be great, of course. The example I'm going to show you is the first ASP that we will see, and I have to talk you through it. And it is a real formula, which is about roots. Here you see in red a root. A root consists of different sections. There's also a green root, and of course there is protection against other trains crossing a certain route. It must be safe. So this red route can only be traveled on when all sections are free, for example. And this is expressed in this formula here. So this is a piece of ASP, ASP programming, and it basically the most important thing is to look for this symbol here, the colon and the dash, which means if. That's the easiest thing, I think. And it has a head, which is here. It says, I'm sorry, that's Dutch, but it says normaal voorwaarde. It means normal condition, which actually says this is a condition under which a train is allowed to drive a certain section or a certain route. And it has two parameters which are variables, and you can see that you can tell that they are variables because they start with a capital. It's as simple as that. That's just a rule in the language. So T is just time. Everything is explicitly set in time. And the second is rijweg, which is Dutch for a route. So when is this condition for this route on a certain time, when is it true? Well, here follow 6 conditions. And these are just enumerated with a comma. That's it. And this is a conjunction. So and. The first two are really easy, because the first one means that the route actually has to be selected by someone. There's these control towers, and someone has to say, I want to travel that route of a certain train, so it has to be selected. The second one is called BGZ, which is an acronym that no one knows what it means, but it is important. I still don't know everything about railway interlocking, but that has to be true as well. And down here is these last 4 are a bit special, and I am only explaining the first one because the other ones are analog. Here we have sets, and basically each line is a set, and you can read the column as the mathematical such that notation. So basically it's a set, which means that it contains all these section-free predicates. such that, and then this predicate holds. And what you see here is that the predicates on the right are typically more or less static predicates that say something about, example, this root consists of these sections. So there may be multiple of these root section combinations. And for each of them, this section has to be free. Now, this is a set which might expand to 0, 1, or 2, or any number of elements, and they're all, again, in a conjunction. So basically, this can be a very large conjunction of conditions that all need to be true. These are really the interesting things. If you go from 0 order to first order, then that means that you add variables to the language. And if you go from first order to second order logic, then the idea is that you have sets to work with. If you look at this, I hope you do share the feeling that I have, that this you must have unit tests. I mean, how can you ever work with such a formula without tests? I mean, it is a conjunction, yes, but there are 4 conditions, no less. And you really need to test that. So when I see this, I really can't continue without having some form of testing. So, in-source testing, I thought it was a nice idea. Let's see if it works here in ASP as well. But what is it? Well, it's just the idea that you put your test right in your code, everywhere. For example, you define a function, right under the function you have a test for that function. You can also add them in classes or any sort of compilation unit you can think of. You put your test right in there. Here's a small snippet from a piece of code, actually also from the railway program I wrote. It's a very small function. And a few lines below you have here an add test, which is actually a test for the function above. And it's like that. It's just so close together. Well, I haven't been the only one thinking about those ideas. And since a couple of months, 1 or 2 months, there start to appear blogs about the idea of in-source testing. And until then, you could find some examples on the internet. I have collected here 4 of here. One is Python. That's the one I wrote myself. But people do it in TypeScript as well, using the PyTest framework. You could do it in Rust. And Clojure is actually the very, very first time, a couple of years ago, that had this with test predicate here that allows you to combine a definition for a function with a few simple asserts. And it wasn't called in-source testing in-source testing at that time, but it actually was. Today we have it in ASP, and it looks like this. I am going to explain this in a separate slide, just make it a little bit easier. Because again, we will have some ASP to learn. In ASP, there is at least the kind of ASP I'm using. There is a hash program for defining separate procedures or programs or things like that. I don't know how to call it exactly, but they call it a program, so I call it a program. And you can add dependencies here. So if this program depends on these other programs, for example, for setting up things or some base knowledge, then you can put it over there. Then I have to introduce facts. Here are a couple of facts in these lines. And a fact is just a statement without the if. So there's no if on those lines. It just ends with a dot. And that means it's just a fact. This fact looks rather complicated because it looks a bit like a function. It has a 0 as an argument and a rijweg, route 32. But these are not variables. So they are just literal facts, and you can just assume they are true. Same holds for the BGZ and for the section 3. But the section 3 I've used a shortcut notation, which you will see quite a lot. So that's why I'm introducing it here. It actually, if you use the semicolon here, then this will be expanded to three different rules. With one for the A, one for the B, and one for the C. The semicolon somehow splashes out the values that it contains or separates. So what I'm doing here is I'm basically setting up the input. I say, well, there is someone is wanting to drive this route on time 0. It is safe. That is what BGZ actually means. And the sections are free. The A, B, and C are free. And now I have an assert here that says that the normal condition H for this route on time 0 must be true. And that's just a normal rule, but I use it as a test by calling it assert. That's, well, I call it assert, you can call it anything, as long as you use the add all. And add all is a call to Python, which just carries out the Python function and returns the result. And why I'm using this is that if you call all with this little text here, then the Python code knows that there is an assert being created. So it can check afterwards if this assert is actually true. And what's also interesting is quite important, answer set programming works with answer sets. So it's a logic language, so it finds logical solutions to certain problems, but it can find multiple solutions, and each solution is called an answer set or a model. It's basically the same thing. And this test also specifies I expect exactly one model. It could be 0, could be 3, could be anything, but you have to tell them. Because otherwise, if it doesn't yield any models, then none of the tests will be executed. That's one of the caveats that you have to know about. Why do I like in source? We can discuss that maybe later. But the most important thing to me is that you have your tests really next to your code, so you can refer easily to them. And you don't have any problems with refactoring. I do a lot of refactoring, and if you have a large test program next to your actual program, and you want to change code and you move code around in your actual program, you have to apply those moves and change all the imports in your test program. And that's prohibiting me from doing the refactorings I want to do. So with in-source testing, you just copy, paste, and move around, and you don't have to think about it anymore. But there are more. Some more ASP. I prepared a few examples, and they are all in the code base and materials that you may have been downloading. Because there's a little bit more I have to explain. We've seen a lot already. And let's begin with the file called soda, which is basically a very, very simple model for having a drink, determining when you get drunk or not. We could do better probably, but if you run this, then it gives you this answer. And here you can see that it has found 3 answers, or 3 models. One answer says, well, you could drink a soda. The second is you could drink wine, but then you will be drunk. And the third answer is you could drink beer, but you also get drunk. That's it. How do you do that? Well, here, the first line, we have what we call a choice rule. A choice rule is when the head of a rule, so the left part of a if, in this case there isn't even an if, it's just a fact, but I have multiple facts separated by a semicolon, and then that means there's a choice. So the ASP runtime will choose one of them. And this is a very, very important thing to have, because without choice, you don't have to search, and you have to find something, there's nothing to do. So this is really important. And there are two very simple rules. You get drunk if you have a beer or if you have wine. Here you see a disjunction. The conjunction you just write by separating multiple clauses with commas. If you want to have a disjunction, an or, then you write multiple lines for the same thing. So it's an interesting language because the designers of the language really tried to make the language easy without lots of brackets, easy to understand, and this is one of the outcomes of that. Then there's also party. There are many interesting things you can do with party. I have prepared some things called party 2. You can do a lot of things already with this simple little toy program. Here I've defined beverages which combine a drink with an alcohol percentage. And we have another choice, or a type of choice, which is a set, because it has these brackets. But this works slightly different from the choice we have here, because this set can contain any element from 0 to infinite. Where this line is just, it chooses 1, always 1, exactly 1. Here it can be 0 or 1 or 2 or 3. Well, in this case only 0 or 1, because there is only one element in the set. So basically this allows the system to party or not. That's the choice it can make. And then again, it can make a choice to drink something, but only if you have a party. So if you have a party and there are some beverages, then you can choose one to drink. And that gives, I don't have the output here, so if you want to see it, then you have to look at your own laptop, or later after lunch you can show it. And then there is the show directive, which says if you find a model, then show me the party predicate with an arity of 0, which basically tells you that there is a party or not, and show me the drink with an arity of 2, which means that it shows these drink things, and it doesn't show, for example, the beverages, because that would give you a huge amount of output. This is basically what it looks like, and now we have almost seen all the things that we need for this presentation. Here are still a bit more things. I'm only picking out what we didn't cover yet, but this contains almost everything. Let's see, I've written down what I didn't cover. Oh yeah. We have the constraint here. The constraint is a bit hard to understand at first, because it is written as a rule without a head. And if you go to the ones who created this, they have a logic that is quite sound, and that makes perfectly clear that if you have a rule without a head, that most logically turns into a constraint. But that's very hard to grasp why that is. And it's much easier to think of this as a saying it cannot be that, and then fill in the clauses that you find here. So in this case, it cannot be that there is a drink BE and A is 0. And that basically means A is the alcohol percentage. And this says the constraint is there may not be a drink and A is 0. That's basically the way you have to think about it. So if everything is true, then the constraint fails. That's another way of looking at it. Maybe that helps you better. It didn't help me. And finally, we have aggregates, which are a special way of dealing with sets. That's on this line. Here's an aggregate. It's written as a set. As you can see here, there's the such that notation. And it's surrounded by curly braces. But there is something more about it. And you say that T is. And this means that it implicitly applies a function to the set which is its cardinality, so they call it count. And if you say T is, then a T becomes the size of the set, the amount of elements, or the cardinality in the set. This is used quite a lot in testing. We'll see later. So this is, you really have to understand this. But it's a mathematical set notation, and you just calculate the amount of elements.
So that gives you the set of beers that have got more than 5% alcohol. Do I understand that right?
Yes, because this is the condition, and it must be more than, and it's also, it's the collection of, or the amount of specials that you have. That's the end result. So.
Yeah, but it gives you the set of special beers.
Yes, this is the set of special beers, but because we use it this way, if T equals, it's translated into an aggregate and counted. So the end result is specials 2. The implementation I'm using for ASP is from Potassco, which is an initiative of University of Potsdam. If you like this topic, it's really worthwhile to go there, because they have all their materials online. They created them during the COVID pandemic, and they're still there, so you can follow everything as if you're actually having a university college class over there. It's very, very, very interesting, and these guys are also very nice and explain it very well. What they created is, and I'm going quickly over this because the most important thing that you have to remember is that if you have this file here, which is an ASP file, it goes to a grounder and then goes to a solver and then gives you the answers. And the answers are basically, well, a number of things we already have seen, like specials 2. That's one of the parts of an answer. And the important thing is to understand that there is grounding and there is solving. And grounding is basically the process of removing all variables. So when you write a logic program using variables, then the grounder says, well, I'm going to look to all the possible values of these variables, and I translate that into all kinds of rules for each value that I find. And then it starts solving. The interesting thing is that there's lots and lots and lots of possibilities to do your own coding in and around ASP. You can create a Python program and control all the things that need to happen during grounding and solving yourself. You can also let that be done by the standard Clingo, which is their program, standard program, but then have call outs for add functions, which we already have seen. You can register observers that observe the grounding process, and you can register propagators that deal with the solving process. So there's not much you cannot do. It's really, really powerful and well worked out. Here we have another test. This is a test about the cases that I've prepared for you for the second part of this tutorial, which is about a graph and nodes. I'm really sorry that's a toy problem, because I tried to present you with a real problem, but that's really too hard, because I had to introduce too many different things. But this is one test. It says test a small graph of 3 nodes, and then it gives you 3 facts, 3 edges, which is basically an edge from one node to another node at a certain cost. That's basically what an edge means. And I have 3 of them. And basically, it's a loop. I think you don't have to draw that. You can see that from the definitions yourself. And then what I do is assert that I have 3 nodes. And I write that as follows. And here we see this aggregation again. I write node n. And what it will do is it will just fill in all the possible values for n. So this will become a set of 3 elements. and then it will count those elements and say, oh, it's 3 or not. At least that is what the test is verifying. Here we have also this number of steps. The solution in this circle has 3 steps, of course, because it's very simple, and there's only one solution. These steps are from 1 to 2, from 2 to 3, and from 3 to 1. And here you see this splashing operator, the semicolon. Here's actually, I could have written 3 step predicates here, but I wrote 1 step predicate, and I used a semicolon to translate that into 3 different steps. Is also 3, and at the end I verify that there's only one model, because there are no different routes or whatever. It can't just ever find just one model.
I don't quite understand what that step represents.
A step is basically it's part of the solution. I forgot to tell, but we will see later in the actual program that you give it a graph, and then it finds steps, a path through the graph, and this path is built up from steps. And in this case,
nodes and steps are part of the language.
Yeah, for graphs, but it's a domain. I've written it all myself. We will see that later. One thing I have to explain here, that is the all and the any. You can see there is an all. In this case, it doesn't matter actually what is there, but sometimes you have to differentiate. All means that in every solution that it is going to produce, the number of nodes is 3. I mean, that's an invariant, that never changes. So if it were to find three paths, then in every path the amount of nodes must be 3. But here I use any, which actually means there must be any of the solutions you found, any of the models you find, must have this as a truth. Now, in this case, there's only one model, so this doesn't make any sense. But we'll see later that it's really important to make this distinction between any and all. Basically, says if you produce 3 models, then all of them have to have this information. If you use any, they say there must be at least one model that has this information.
Question.
Yeah.
Your asserts your asserts are your in programming testing.
Yes. Yeah.
Well,
actually, I call this a test, the whole program.
the whole thing.
This is a test, and this test consists of different asserts. That's more or less a distinction.
Okay, and your hash program at the beginning, is that just labeling this?
Yeah, it's like defining a procedure or subprogramming or.
Okay, thank you.
And you can do this in one file. So there's basically, if you look at the files that I create, and that are also in the materials, then there's multiple of these program sections, and the actual logic that you want to test is just above it. We'll see later.
Yep, thank you.
You have to explicitly call this program section.
No, that's done for you. And that's actually part of the next slide, I think. Almost. So how does it work? I already explained that if you have a bit of ASP, it goes to a grounder and a solver. In this case, during grounding, we collect the facts. And this is very important. All these asserts are facts, and they need to be facts. If they're not, you run the risk of them being optimized away. That's one of the biggest caveats of logic programming, that you can write down things and they never become true, so they will never be tested. And we'll come back to that later, because that's really a challenge sometimes. But we do that during grounding, which means there's no solving at all. It's just asserts are just facts. That's it. And then after the solver has produced models, then we check and report if in these models these facts are present like we expect them to be present. And this I've created a lot of this yellow code to actually do that. And this code is in heavy development, so if something goes wrong, then don't be surprised. The problem I prepared for you still have 24 minutes, is the Hamiltonian path. I'm really sorry this is such a simple, well-known problem, but that's also the reason why I selected it. Because I think most of you are quite familiar with this, and if not, you're at least familiar with graphs and nodes and things like that, so that the problem itself doesn't distract too much from the actual solutions and the use and application of ASP and in-source testing. This Hamiltonian path has 3 solutions, which means that there are 3 paths that visit every node without visiting a node twice. That's the idea. The green path is one of the paths that is possible. As you can see, it visits every node without any node visited twice and without skipping any nodes. And there are basically 3 paths, so this is interesting because it means there will be 3 models when we run the program. But there is a way of selecting these models because we want the shortest or the path with the least costs. And the costs are the numbers that you see here next to the path, here. These costs must be minimized, and that's also one of the things that ASP can do for us, and which we of course want to test. I have a little bit more time than expected, so that's very good because I want to explain to you now the actual code that has the solution and has all the tests. And maybe we could even start coding before the lunch, so we'll see. Is this readable actually? Because if not, if you have checked out the code or started the code space on GitHub, then there's also a way to find this in your local laptop. And I'm going to switch anyway because I see that it's not all visible there. But we'll start with a lot of information, so please bear with me. The first thing we see is that it's actually divided in 2 different sections. One of them is this upper part, which we call the problem instance. And the second part is everything below, which we call the problem encoding. And think of that as an object and a class or something like that. This describes a class of problems, and this describes just one instance of a problem. Actually, the problem instance is only this piece, and these are asserts about the problem instance. So that's here you already see that the in-source tests are very, very fine-grained. It's not per se that you write a test for a whole program. It's not even the case that you write a test for your problem encoding. You could even write tests for your problem instance. So you can take very, very little steps to make sure that everything is okay. And I really use this a lot because this railway stuff is really complicated. And then at some point it doesn't produce the correct formulas. And then I think, well, where could that be wrong? And then you start building up these very small steps. Okay, let's first assert this assumption. Is that actually true? Okay, but then that must also be true. And so you build this up in very little steps. And I'm usually able to very quickly pinpoint the source of a problem. Most of the times you will have these in separate files, of course, not in the same file. But we start out with them in the same file to make it easy. What we do here is we have these all these edges, and these edges describe this network that we just saw. Oh, I hope you believe me. You of course check it if you want to, but these are all the edges that are in this graph. Again, just a node number, another node number, and then the costs. And then I started doing some asserts, just to make sure that I've done everything right. Well, what did I assert? I said, well, I think, having defined this, that there must be 6 nodes. This is actually already testing this here, because the node is only defined here. But I felt it more being a part of this piece, so I'll put it over here. And then it says, well, I can also say something about the incidence of the nodes, meaning the amount of arrows that go in and go out. So what I actually do is, for every node, there must be at least one edge. It's just a sanity check, because if I make a mistake in preparing my instance, and I introduce a node which has no way to get out of this node, I will never get a Hamiltonian path, of course, never get a cycle. So I check this incident in and incident out, because if I have a node, there must also be an edge with n, the node number, in the first position. So it basically says there must be something in the node and there must be an arrow out of the node. I check that here by saying we have node n and we have an edge n, and that leads to an assert. Well, this is very interesting. If you run this on your computer, then you will see that this actually generates 6 lines, 6 asserts. And does anyone already understand why that happens? Yes, right. Yeah. That's one of the things that that ASP does for you during the grinding. It takes n, it says, oh, n is a variable, what are all the possible values for this variable? And I recreate this line for every instance of this variable. So it will be 6 asserts. Now, this is also a bit tricky because I included the n here, because when I don't, the head of each of these asserts, meaning the part left of the if, is 6 times the same, which means I get a conjunction, which means it will almost always be true if any of these nodes has the proper edge. But I want each node to have a proper edge, so that's why I included n here. So when ASP starts replicating this rule, it will also replicate the head and create different heads for each node n. I also say something about the costs. I say, well, the cost must be somewhere between C, between 0 and 10. That's completely arbitrary, of course, but suppose I made a mistake and write something negative or a string or do something crazy. I know myself, so I like to write tests for this and these kind of things. And then here, the last thing is also interesting because it says, well, I want to see the minimum cost of this thing, and it must be less than 12. That's another way of saying I already know a bit about it, so I can assert this. And here you see an aggregation, which is important to see that it is slightly different as the aggregations we already have seen. This is a normal part of an aggregation because it has this semicolon, which means such that. It's just a set notation. But then what goes in the set? In the set goes a tuple of 3 values, C, E, and B. And why are we doing that? Why not just sum up the costs? Why do we sum up these tuples? Well, if you were only to take C here, then you would create a set of different C's, which are 1, 2, 3, 1, 2, 2, 3, which are not unique. So if you create a set of that, you would remove all duplicates and you wouldn't have a cost. So this tuple of C and A and B will make each set entry unique. And the sum function is so smart as to take only the first value of the tuple to actually sum up. Yeah, it's the same thing. They call it the tuple, but it's a triple. Yeah.
In this case.
Yeah. Or a triplet. You know. Now we go to the problem encoding. This is actually where it gets fun, because how do you actually encode such a problem in ASP? Well, what I did here is first I do some little preparation, because I think it's interesting to be able to reason about nodes. and not per se about edges. So I introduced here two rules that say, well, if there is an edge from node n to wherever, this is the underscore means whatever, it's basically a wildcard. Also the costs I really don't care about, but I know that if this edge is there, then there must be a node n. But if this edge is here in the incoming part of the edge declaration, then there's also node n. This might lead to some duplicates, of course, but I don't really care because, well, it's logic. And this is a disjunction because I mentioned here node n and node n. There's 2 times exactly the same head, which means that these are basically, but this is an OR. And what we then do is a very, what they call easy ASP programming. The easiest way to attack a problem is by first generating all the possible solutions. And we do so by creating steps. But you can see here that this is a choice. Because there's this semicolon here, which means that this is actually a set again, and it chooses one element of this set because we left out the curly brackets. It's a bit hard, but this is the way the notation works. And it says basically if there's an edge AB, then we can choose to start our cycle there. And this is really arbitrary. I mean, it can be any A, it can be any B, and it can be any step.
You have no difficulty with these edge and node. Are they somehow predefined, or is this the definition? Yeah.
No.
So, edge and node and step, are these really defined here? So, what a step is really defined by saying, well, there must be an edge such that, and what an edge is really defined by those facts above, or?
Yes. That's typical for a logic language that you just say A and then A exists. It's there. It's true.
Okay.
So basically, anything that we mention here, we call them facts. They are true, and you don't have to declare types or whatever. Just say this, and that's okay. And we reuse that here. And actually, if you fail to have edges in your program, then it will complain. So, well, you expect there to be some edges, but there aren't. So please fix that. This introduces new things. So you could use any name you want. Yeah. So this will introduce new steps. Actually, this chooses one step to start with.
So you could say the definition of a node n is that there's some fact edge with that n in it.
Yes.
Okay, all right, I understand.
Node n is basically true or part of the model if there is an edge with n on that location. That's basically what it says, yeah. Okay, so here is more or less the same. The only difference between step and node is that I used one more variable, A and B. And here's the interesting thing. Here we make a recursive rule. We say if you have a step, AB, that's right of the if, this is called the body, that part. If we have a step AB, then we could choose another step, which we can see again because of this semicolon over here, which means it is again a choice. And it can choose step BC. But there are conditions. These are important, of course. And these conditions is that there must be an edge, BC. B is, of course, the end of the step that we have here. So we have taken one step to B, then it means that we might take from another step from B forward. But we don't want to go back. So if we arrive at B, we don't like to go back to A again. So we say here that C must not be equal to A. You don't want to go back. And this is basically the generation step. And you could, what I always did is run my program here and then see what the results were. But you quickly get bored about that because you have to scan your output and there's lots of information. And when one thing is missing, it's very hard to spot. So I'll actually go over that. I'll switch my terminals, and then we can look at the real code, and then I'll run the examples, and then we can see what I'm talking about. And everything I do here, you can do it on your laptop as well. Yeah, of course, never at the display as you are. Yes. Sorry, this is really hard. Use as mirror. Good. This way. I still need the slides because all the solutions are actually in the slides. And yeah. Hey, I can switch. Cool. Okay. That's interesting. Here's the code. Yes. I think it's rather big enough. Maybe I can make it smaller. Is that okay, you think? For the people in the back? Because then there will be more on the screen. Thank you. Same holds for here. Let's see, what was my last command here? Yeah, the last thing I did, I was running the Clingo. Clingo is basically the ASP processor of the Potassco implementation. And I'm running Hamiltonian cycle 1, which is included in the materials. What I did here, sorry, I have to explain a bit more about the code. Go away. I have to explain a bit more about the code, so you have an idea how it works. Here we have the generation part. You can see my mouse cursor if I do this. Okay. And we were left off with this recursive rule on line 23. And then there is an important extra thing we have to do, because now we can recursively define all kinds of paths, which is completely random. But we have to specify somehow what we actually mean by a Hamiltonian cycle and when the conditions have been fulfilled. And for that we need a path predicate. So I define a path. This is really my invention. It's nothing predefined or whatever. I just define it here. A path, and I say, well, a path B, I have a path B if there is a step to B. That's basically what it says on line 26. That sounds natural, I think, if you say that. If you take a step to B, then there is a path to B. But I want to extend that notion a bit, so I make it recursive on line 27. And that line says, well, if you have a path B and you have a step B to C, then it means I also have a path to C. That's basically navigation 101, right? And these two conditions make sure that I have something to check to see if the path actually covers all the nodes, because that's what we want. And we do that by applying a constraint, and that is the third step in what they call easy ASP. First you generate all the possibilities, and then when you're done, you start weeding. And by weeding you do with constraints. So we apply a constraint here. And again, it's not, seeing it the first time is not that intuitive, but if you repeat for yourself, it cannot be that. That really works. So it cannot be that there is a node n, and there is not a path to n. Does that sound reasonable?
But where does the path begin?
At any step, it doesn't really matter. Can begin anywhere. We haven't any, in our problem definition, we didn't say anything about where it had to start, right? So it just chooses a step and then begins there.
Could you start again on the constraint, please?
Yeah, the constraint. Now what actually happens is that it starts producing models, solutions. And these solutions are along the lines that we discussed here with these steps and these paths. But then it creates thousands of solutions, because this little graph can be traversed in many ways, extremely many ways. But we have to say, well, there's only a few of those solutions that are the correct ones. So we have to weed out the solutions that are not the correct ones. And we do that by saying, well, if you have a solution, then this is the constraint. And if this constraint fails, or triggers, or how did you call it, then this solution isn't valid. That's basically what the constraint is saying. So at some point, it makes up a very nice route, but it skips one node. And this constraint said, well, there cannot be a node that without a path. So that will reject the majority of all the false solutions. And this is really interesting way of thinking, that you just generate a whole bunch. You get all kinds of different solutions because there are many choices to be made by the system. And then at the end say, oh, but these are the correct choices.
No, these are the incorrect choices.
These are the, yeah, thank you, yes, right. And then the last thing we have here is a minimize directive, which minimize is also a function on a aggregate. And we have a set here where we again see that there is a tuple or a triple. Oh, that doesn't work anymore. We have a triple here. We collect costs A and B in a set. We've seen that before in our tests. We did the same thing in our test. We collect all the costs. We add them up to see if they're within a certain range. Here, we are not interested in a certain range, but here we are telling the ASP system that we want to minimize on the cost. And we do that by basically having the same aggregate that supplies the information about the costs, but we say with hash minimize, well, try to minimize the value for this set.
So that returns one value, the smallest with the smallest c.
Yeah.
One element of the set.
No, not really.
I'm sorry.
Almost. What this does is, for every model. Oh, yeah, I can repeat your question.
Yeah. So what I asked was if this selects the element from the set with the smallest possible c.
Well, the set actually contains a little bit more. For each model it finds, it calculates this set, and the set will contain a tuple with the information of all the steps taken. So basically it replicates the A, B, and C from the edge, but in a different order. It says C, E, and B, but that's because the minimize function is also taking the first element of the tuple. This is the tuple. Taking the first element to do the actual minimization, and A and B are only here to make the values unique. Otherwise, there is a set of costs 1, 2, 3, 2, 1, 1, 3. So it calculates the set for every model, and then it knows the value, it sums them up, and it starts looking for the model with the lowest value.
Where is that happening? Where is, I don't see a less than A less than B, or.
Well, that's what
That's what the minimize function does, and it's.
Oh, that's a function, so that you're not declaring something there, you're
Did-
invoking something.
Yeah.
No, yeah, this is built in ASP.
Oh, okay, so
Sorry.
you're invoking a function there.
Yeah.
Oh, okay,
Yeah,
I
yeah,
thought
yeah.
you were still declaring, okay.
No, sorry, yeah. Good point.
Erik, does it mean that everything with a hash is a function? So a hash program
Yeah,
means
or the-
something? It's
No, it's basically a directive. And there are magic values, so to say. And in this case, hash minimize just means that minimization has to take place. It's not really a function. It's it's a directive, actually. You could also write this differently in a syntax that you add to the rules that it applies to. But I find that even harder to understand, so I usually use this syntax. And yeah, think of it as a directive. That's it.
maybe this is a good moment for lunch.
Yes. Good. Yeah, this time, I see that.
Okay.
So after lunch, we will run these tests and go through some exercises that you are able to do. And basically, we have Hamilton cycle in 3 variants, and we take them from 1 to 2 with a few fixes, and then from 2 to 3 with a few fixes, and even 3 has a challenge left for you to do in the train or when you are at home later. Zo. Oeh, dat gaat behoorlijk hard. Dankjewel, Pieter. We waren net gebleven bij...
In English, please.
Sorry, thank you. Excuse me. We left off with the Hamilton cycle problems. And I was busy talking you through the first iteration, Hamilton cycle number 1. And that contains actually the algorithm, and that will not change. But the way of testing will change, and we go to 3 iterations, Hamilton cycle 1, 2, and 3. And we are currently looking at 1. And the tests are a bit different than the tests we will be seeing in the next slides, because we keep on improving. This is the very first iteration of tests that I actually don't use anymore. But I want to show you this to make you aware of certain problems and make you a bit aware of how it actually works. We'll see here that we have some asserts. Just to be sure, this is the same file as that the problem encoding is part of and the problem instance, so it's all in just one file. And we here have some tests which I call assert. Some things are a bit familiar because I have already showed you some asserts in the presentation, so I don't go over them all in detail. But I want you to note that it says assert, 6 nodes, and this is completely deliberate. I mean, I could call it anything else. I just use assert because that speaks of some intention, that reveals my intention of what I want to do here. But actually I could use any name here. There's nothing that makes this obligatory or whatever. What happens is I define a fact, or almost a fact, that I call assert 6 nodes. But it isn't a fact. It is a fact that depends on a simple body. And this body is in this case a thing that counts the nodes. And it's really important that this is simple, because if you make a very complicated thing over there, a very complicated body, then it might be the case that the body doesn't hold and you don't know exactly why. So you want to know, you want to keep this really, really simple. And that also has to do with optimization that is being done by the grounder. I told you the grounder takes away all the variables and fills in the possible values for these variables. But the grounder also can just skip rules if it finds out that the body is always false. And if that happens, then this fact assert won't be there. So one of the things that are not possible is the use of not in the body. That's why I'm using here, for example, this actually says that there is the amount of edges from n to n, basically an edge from a node to itself, is 0. I could also have written not edge n n dash, but that not will be optimized away. And that I don't want, of course. So this is one of the things you see a lot, this notation with a set which must be equal to 0. Still there is a problem because suppose that one of the tests fails. We said assert 6 nodes. Well, we don't have 6 nodes, we have 5. And then this rule doesn't fire, or isn't true. So assert 6 nodes isn't also true. And answer set programming is based on stable models, which means that there is a minimum model that contains all the atoms, they call it, that must be true to satisfy your program. And this model does not contain things that are false. So it contains only the things that are true. So as soon as assert 6 nodes isn't true because the number of nodes is 5, then it isn't part of the model. And if it isn't part of the model, we just don't know what happened. It hasn't been there or not. You just don't know. So this doesn't work on its own. What we have to do is, in this case, on line 50, I have an ensure. And this is obligatory because ensure is taken by the tooling, and that says, I want to ensure that these predicates are present in the end results. So there's basically a second layer that you have to apply to make that happen. Because if you don't, you can already try that. If you look at the lower window, I run the Hamilton cycle 1 with Clingo. And what it actually does, it calculates the model. Well, try that again. Oh, here. Wait a minute, that's in the wrong direction. Clingo says there are 3 answers. Here's answer 1. And you see the assert 6 nodes is part of the answer. Well, it's of course no way of testing if you have to verify that yourself all the time. That doesn't work. So it's nice to begin or nice for debugging, but it's not really a sound way of testing because unit testing always implies automated tests. So what we do for that, to fix that, is we made the ensure. That was not, yeah, this is better. I created an ensure, and the ensure is something that is interpreted by a little program that checks your model and sees, oh, there is an ensure, and this ensure contains some asserts that have to be present, so I'm going to check if they are present and warn you if they are not. And that, of course, Clingo doesn't do that for us, because Clingo doesn't know about ensure. Ensure is something I made up myself. It's just a fact. It isn't even there. Weird. So, if I want to enable the use of ensure, then I have to not use Clingo, but ASP test. Sorry. And what that actually does, it says, it runs all the unit tests in Python. You can skip that by using - silent, a bit quicker. And it says here that there is an assertion error and the steps test fails. And it does that because it knows from the ensure statement which asserts must be present. Now, there's a couple of problems with this approach. By the way, if you see this last error message, you can ignore. It's a work in progress, and it still gives this. This is a bit problematic, because you have to basically repeat every assert that you have and mention it again, which you will forget at some point. So it's not really fun. Another thing is that, as you can see here, there are in asserts are also things mentioned that have an n, a variable in the name. But if you don't supply ASP with a certain source of this variable, then it complains that it doesn't know the variable and doesn't know how to fill it in. Remember, the grounding fills in all the concrete values. So that's why it says node n, and this ensure is only true if there is a node n. But here it's getting a bit sketchy, because here again, if this body is a bit too complicated and will not be true, then also your ensure is completely gone from your program. So this is basically what I call a ad hoc way of testing, and sometimes I use it because you're just in between your code and you just want to know something for more or less for debugging. But for real automated testing, this is not a good approach. Also, this is one of the questions. It says here, the steps test fails. We've seen it here, failed assert steps. I want you to take a look at this test and see if you know why it actually fails. You can do that in your laptop, or you can look at the code here. It's this test here. Someone want a hint? It has to do something with the next line.
Is it syntax? Or?
No, it's not syntax. It has to do with the next line, line 48. That's a hint, yeah. Oh, there's the... Oh, okay.
Yeah. Okay. Now, is it because it's sampling not enough models for the steps to be in there? Okay.
It has to do with the fact that, remember this Hamiltonian cycle, there are three possibilities for it. So it generates three models. And each model is a solution for the program as specified here. And part of that program is this assert. But this assert is part of every program. Of every model, so to say.
So it doesn't exist in two of the models.
Exactly. It doesn't exist in all models. Exactly this path, I hope it's, yeah. Exactly this path, because I've been very specific. This path is only present in one model. And you could solve it. You could make a conjunction of it, but that's not really a good solving, I think.
But you solved it on line 47. You did that by hand, or did you just, from a unit test perspective, you looked at a set of results and you plucked that out of the set of results as one of the new assertions? So, how did you know? How did you author line 47?
Sorry, I don't understand your question.
The particular path that is described in line 47.
Yes?
Did you think of that, or did you take that from the answer set?
I took that from the answer set.
From
yes.
a previous run?
Yeah,
okay.
yeah. But this is quite also a limitation of the way of ad hoc testing like this. You cannot differentiate between the models. And again, you could make a disjunction of it by repeating these rules with three different steps, but then it's a bit coarse, because that will be true in any case, and you could do it. But I think it's not really solvable, and we have to look at a slightly other approach that you've already seen. which is basically part of Hamiltonian cycle 2. Let's go to that. Sorry, I have to type with one hand now.
You might be live again.
Yeah, I think you're live again, actually.
Am I live? Oh, yeah. Oh, good. Great. Thanks for fixing. And we go to the next one. 2. One thing to notice here, that at the top, the problem instance is gone. It's now separate. And that's, of course, a good idea, because making your problem instance part of your problem encoding is not really a smart thing to do. The tests are also gone. The tests are now here. And these look like the tests I have shown you earlier. These are created with the hash program directive. And the only thing that my little program does is just check for a program that starts with the name, the word test. And it says, well, this is interesting. I take this program, I combine it with everything that's not in a program, that is called base. So if you look at the top here, there's never a program declaration. This is just a big space where everything is that is not in a program. That is called base. And our tests usually refer to that. So the test depends on base, which says I want to have all the logic that is not specified elsewhere. The test could also specify other programs, like we do here, general checks, which is the program just above, which is not a test because it doesn't start with test. And it includes that one and then starts to do the test. You see that I have moved the problem instance to this test. So the problem instance is this big graph, and basically checks if the minimum steps is 6. And there are 3 models. What we can do now is we can make simpler tests, and that's what you always want. These big things are very hard to actually debug if your test fails somehow. So that's what the next test does. It says test small graph of 3 nodes. And here's exactly what you want with testing. You want to create little nodes, a few nodes, little things, do a sort of pseudo induction testing, like say if it works for a very basic situation and I can expand it one step, then it works for all situations, like that. And that's what's happening here. Still, there are some problems. And these are outlined below, because there is also nog a test minimal graph, which says there's a graph of only 2 nodes. And here's a little challenge for you. If you run this, then you see that there is a warning and there is a failure. And maybe you can fix that. So have a look at it for a couple of minutes.
This is 2.
Yeah, this is Hamiltonian cycle 2. I can show you the problems here. It says this warning. The assert number of steps is a duplication. I think you should be able to fix it. And it says that it has successfully tested the big one. That's our original test, which contained 38 asserts and yielded 3 models. But it failed here at cycle cost, and that is part of the test small graph of 3 nodes. And to help us a little bit, it printed the model it found. So these are the steps it found, but the assert is failing. So that's not part of the solution.
Yeah, okay. Well, I think I found it.
Oh, great. Tell us.
Cycle cost has to
Could you speak in the box?
cycle test has to be between 10 and 100. And in a small model, it's too small for the main model constraint.
Yes. That is, where is the cycle test? This one. Say 0, 1.
Yeah, but now you're tweaking your program to fit the test data.
Actually, I'm fixing the test.
No, you've just. Oh, it's an assertion.
It's an assertion. It was a bit too strict.
Okay, but why have a range in the first place other than an exercise?
Just to have something to fill.
Okay, fine.
Not everything has to be hard. That's better. Now the warning. Someone figured out what the warning is about? A certain number of steps. It is, oh, sorry. Try to highlight it for you here. It's actually a bit of a repeat. We've already seen this. Yeah.
I think it's to...
Here.
Now the microphone is on the way.
I think the assert needs an N in there as well, but I don't quite know how.
Yeah, okay. That's right. The easiest thing is adding it here. Oh, wait a minute. What it actually did is it made a big conjunction or disjunction of this formula. So it repeated the whole line twice, but the head was the same in both cases. So then you get a disjunction and say, well, this or that is both okay. That's not what you want. You want to have two asserts. Okay, now I have another problem. Someone knows how to fix? No, I didn't explain this. I'm sorry, but yeah, I did a bit. Yeah, I did explain it. I did. It now says that N is unsafe. I didn't mention the concept of unsafe, but it just says, well, I have a variable N. I don't know values for it. And it wants to ground, which means it wants to fill in the different values, possible values for N. But there isn't no N. Yes, that's right. That's the solution, yeah. This way we say, well, this one holds if there's a node n, and by doing so, we also provide ASP with the notion where it can find possible values.
So what's the can you explain unsafe?
Yes, well, maybe no. No, it's a bit of a hard concept, and I probably can explain it, but not in a short time. But what it means, it's just not possible to bind it to some concrete value. It just doesn't know.
It's a free variable.
Yeah, more or less, yeah. If you go to the website and they have these online colleges, online, call it in English, courses, and they explain it everything very well, with very good foundational logics that I cannot repeat here. Hopefully this is okay.
It's worse.
No, it's even worse, yeah. I'm sorry. Why is it worse? I have to look at my own solutions because it's a bit too hard to do that online.
I think you fixed the wrong one. Maybe?
Oh, yeah. I think that one I have to fix. Yes. So, I'm really sorry. This is, it has the concept of global and local variables in a rule. So n is basically a rule global variable, while each aggregation or each set, like here, has its own variables. So A and B are basically not of any consequence either. I could have written this, which is basically better to do, because there are don't cares. Oh. And by using n in the head, I have overwritten the n in the last set. If you use a wildcard and I get all the noders, if I use n, then n now is defined by the head, which also contains n as well. There's only one n. So this is basically how it works, and you can see now that it here says, well, it logs all the. It's still, by the way, another error, but it logs the tests. It says I've tested the big one, test small graph. It says how many asserts there are. You see there are quite a lot. That's because of grounding. In all the combinations of possible values, it works out into separate rules and might work out to separate asserts. Here there's 18. Well, I've written only 1 or 2, right? It also tells me how many models it has found, so I have a clue that everything is okay. And then it says test minimal graph has no models found. So go to the test. And this is actually one remaining test. No models found is the reason why I mention the number of models here. Every test has a way of specifying the expected number of models. That's really important, because if there are no models, then all your tests seem to either fail or succeed, but you don't know. So you really want to say, I want to have one model. And in this case, it says, well, your test here didn't find any models at all. And this is a bit more difficult to get it right. Maybe we shouldn't do that right now, because it's rather complicated. You can do that if you want to in a break or something like that, but it's a bit too complicated to do here. That was my third challenge here. The problem instance with only 2 nodes does not work. Fix the code. That's actually, it's doable. But maybe we could skip it. No? Okay, so why does this test fail? Any idea? Why it doesn't generate a model?
Do you have to rule that you can't go back still? From 1 to 2, 2 to 1?
Yeah, it has to do with that, yeah. It really requires a couple of steps, because we have only 2 nodes. And the one that's actually failing, or the one that is actually, there is a how you say that, there is a rule here. The constraint, we can remove the constraint. That's usually what I do. Let's see if that works. And then it says failed, number of steps. These are all failing, of course. I test the big one, so this was not a good idea. Sorry, I prepared this. I have to look at my own slides to see the solution. Huh? And skip it, yeah. So here's the solution for the first one. Here's the solution for the second one. Yeah, and actually, here's the, yeah. Sorry, I now remember that I already knew that I wanted to skip this, so I don't have a solution. I only have a solution at the very end, because this is really the most complicated one. I have to do a couple of things. It is in the slides. It's the last slide here. So we'll skip that and go to Hamiltonian cycle 2. Sorry, that was not. That was a bit. Whatever. We're running out of time? Oh, we have. Okay, then I'll stop. Because I think you've seen enough, probably. If you want to continue, there is still a Hamiltonian cycle 3, which still contains a couple of solutions, but also contains this last problem, including the solutions. And the solutions aren't really complicated, and you all will recognize the small fixes you have to do here and there. But there are multiple, and understanding them is maybe still a bit of a challenge. So I invite you to take it, and I thank you for your attention.